My name is Chanchal Chatterjee. I work for the Google Cloud. I am a cloud AI program manager. I'll be accompanied by Adam Hammond, who is from Quantify, on one of the use cases that we are going to demonstrate here. So today I'm going to talk about model explainability for financial services industry from the perspective of regulations. So we have been doing model explainability for a long time as a community, but there has been a bit of a confusion regarding who the audience is. A lot of us who are developers are very focused on doing model explainability from the standpoint of understanding the model. So today, I'm going to take the perspective away from that. We are going to talk a bit about how the financial industry regulators view model explainability, which is the most critical application of model explainability in the financial industry, and also one of the most critical use of model explainability, period. So moving forward, we are going to learn how financial problems, business critical problems are solved in the area of risk, lending risk, and insurance loss are two use cases we are going to look at, where we'll be explaining the models from a regulator's perspective. All the solutions are built on the Google Cloud Platform, on the Cloud Machine Learning Engine, with complex deep learning models. We'll also demonstrate how we improve the accuracy, but yet we explain the models for regulators. And finally, one of the key pieces is we are going to convert some of these models to a rule-based solution in order to augment existing rules. So if you already have a rule-based solution that is completely approved by the regulators, then you may not want to add a completely new model to the rule. You'd see a lot of your financial services customers ask for additional rules in order to augment their rules and make it better so that the regulation becomes, regulatory approval becomes much easier. So we'll start with a few use cases of model explainability in the financial services industry. We'll also talk about why we want to do model explanations. We want to talk briefly about some methods of model explanation. I think I'm going to squeeze those slides because I don't think that is very, very relevant for sake of time. Then we are going to talk about types of explanations that regulators typically want, and we'll give two examples, one from lending risk, the other from insurance loss, and we'll also talk about a method that Google created in order to augment existing rules. Can everybody hear me well? Yeah. Okay, awesome. So financial services use cases. There are many use cases in financial services which is of high use for high importance for model explainability purposes. So the first one is credit lending. This is a use case we will cover. The main purpose is to comply to regulation, and it's very high importance. Transaction fraud. This is where model explainability is needed in order to create transparency. There are many reasons for it, but I just highlighted one or two key reasons. Anti-money laundering, also transparency. Claims processing. This is where we want to automate the explanations and the decisions so that it's all supported in one transaction. And we also want to create transparency. Investment management, automated trading are also very high degree of use for model explainability and for automated decisions. So the two use cases we will consider, one is lending risk, the other is insurance loss prevention, and Adam will present the insurance loss prevention use case, which he worked on. Why do model explanation? So when developers look at model explanation, we are typically looking at model explanation from the perspective of understanding the model. Whereas when the regulators look at model explanation, they are trying to increase their trust in the model. These are completely different goals. And this is why I made this table. in order to make it clear what the two goals are. The developers look at model explanation to improve performance of the models, whereas regulators look at model explanation in order to reduce bias and increase transparency. Most of our software engineers would look at model explanation in order to create better algorithms, in order to create a better model. Is this a 6-layer ResNet or 10-layer ResNet? Do we do it this way or that way? Well, all these differences are going to come up in model explanation, but regulators want to do model explanation to comply to regulations. And the output for software engineers and developers for model explanation is produce a better model, a better software. But regulators want to produce a better report. So clearly, the two audiences are very different. And therefore, when you look at the regulator's perspective, the entire scope of model explainability changes. And how you do the explainability and how you report are very different. So there's a funny picture which shows why we want to do model explanation, because we want to create transparency, we want to create trust, we want to create a better understanding. And in the US, we have two guidances. One is the SR 11.7 and the OC 2011-12, which are basically guidance for model risk management, but when everybody uses them, then it almost becomes mandatory. GDPR in Europe is very important, and there's two articles that are written, one by SEC and the other by a large number of academic and industry people have written the article together as to how to do the governance of machine learning. So types and methods of machine learning, considering the time I'm going to go through fast on this. So model interpretation has two variants. One is the global, the other is local. Those of you who are practitioners in machine learning know this difference. Global is when we take the entire aggregate of data and we want to give the explanation for the model on the entire collection of data. Local is for a given transaction, like if we are trying to detect fraud, for one transaction that was considered fraudulent, you want to know why you identified that transaction as fraud or no fraud. And it can be a single or a small group of transactions, but local explainability is basically for a limited number of data. So in terms of methods, we saw that there are over 30 methods that are used in the industry, which cover a wide scope of model explainability. I have only identified the key ones that are most commonly used in the industry and that are most common and highly prevalent. So the non-Google ones that are very common are LIME, okay, locally interpretable models. It's mostly a local model. I have a brief description. The second is anchors, which is by the same authors, and SHAP values, which is very common in the industry. In terms of the Google methods, there are two that I want to highlight. One is called integrated gradients, and that one is very common, and that has been used very widely within Google. I'll describe that in a little bit of detail. And the second is called TCAV, quantitative testing and concept activation vector, which is also another model explainability tool that Google has created. So going over these, LIME stands for locally interpretable model-agnostic explanations. And this is primarily a local interpretation method, although there is an extension to global called SP-LIME. The key attributes here is that it generates data in the vicinity of the transaction or the particular data, and then it fits the linear model and explains the linear model. It treats the features as uncorrelated, and the main issue with LIME is excellent in explaining local models, doing a local interpretation of models. But the problem here is that it has to go through the process of generating synthetic data and fitting the results to that. So it creates what we call a surrogate model, which is problematic in some cases. Some regulators will not accept that. And secondly, it takes time to do that. So if we have a large number of transactions happening, 1 million transactions per second, it will be very difficult to apply this type of a complex technique on a transaction-by-transaction basis. The second one is an innovation overline, which is called anchors, which is also a model-agnostic explanation tool. So they basically generates logic and rules around transactions, and these high-precision rules are called anchors, and presents local sufficient conditions for these predictions. I have linked the paper and the GitHub. It's all open source. It's by the same authors that wrote the line. This third one that is publicly available is called SHAP values. It's SHAPly. It basically does the model by comparing features with and without it. You take the feature out, it basically measures the sensitivity of a feature in producing a certain outcome. What is great about SHAPly is that it produces the positive and negative effects on outcomes for different features, and we have some results on that. And because you have to take all combinations of features, if you have, let's say, a model in which you have 2,000 features, then taking different combinations of 2s and 3s and 4 and 5 makes millions of combinations. And therefore, it is very difficult to go through all those combinations, so they make some approximations called Sabas methods and other methods. And what it does is that it finally creates an approximate solution. Nevertheless, SHAPly is an awesome method of doing model explanation and is widely used in the industry, and it is also very fast and accurate in real-time transactions. So coming to the Google methods, the first one is called integrated gradients, which are axiomatic attributions of deep networks. Now this one is also a sensitivity type measure. It is also a local interpretation tool and not geared towards a global interpretation, although you can take a whole bunch of local interpretations, average them together, and call it global. So the basic idea is you perturb the features and inspect the change of the features on the network's prediction. This method has been used in over 20 Google products internally. So let's take a visual example of how this method works. So here's a picture of a fireboat in front of the bridge. So the model says there's a fireboat. So if you look at the far right picture, at this end, you'll see this is the picture of the fireboat, and these are the gradients. So the problem with that is that the gradients doesn't tell you anything because it covers the entire gamut of the bridge and the boat and the ocean and everything. So what we do in this method is we take a baseline picture, which is a near dark picture at the far end, and then we look at the gradients that come out of that picture, and we see some remnants of the bridge. Then as we change the picture intensity from almost dark to the full intensity, different gradients emerge. And as you progress through this different intensity of the picture, and as you see these different gradients, as you integrate through these gradients, then voila, the explanation comes out. And you get a beautiful picture of the gradients that are relevant to the fireboat itself. And that's how the integrated gradient method works. And we also found that the gradients are most relevant during the transition phase rather than the full featured image. And this is an internal paper published and available. So next one is called TCAV. This is a innovation over the axiomatic methods. This creates boundaries of different features in order to judge the sensitivity of the features' effects on the outputs. So these are some of the methods we have for model explanation that are very common. So next, let's look at the types of explanations that regulators will be looking for. The first one that is most common is the importance of the different features. How are the different features important? So if you label the features 1 through 9 or 10, then you see that certain features have a higher importance. The second thing, you also want to look at the standard deviations of those features. That is, it's not just useful to take the average importance, but also how does that importance vary from sample to sample? Like if you have an importance which is let's say 31, but the standard deviation is 20, which means that the importance of that feature varied widely over the samples. So you want to also look at the standard deviations. The second is the positive and negative contributions of features. That is, if certain inputs had a positive effect on the outcome and certain inputs had a negative effect on the outcome. So those are the two important things that a regulator would want. The other two important things are joint contributions of features or inputs. So let's say you had two inputs. One was, let's say, the loan amount, and the second one was the income of the person. How does the loan amount and income relate to each other in terms of the risk of credit lending? So this is, in those two examples, we'll take some examples of how that happens. And the fourth one is, and also we want to see how does an input increase the outcome and how does an input decrease the outcome. And then fourthly, how does the different samples affect the outcome? The different inputs vary from sample to sample in increasing and decreasing the outcome. So let's go through the first example, and then I'll turn over to Adam for the second example, loan risk prediction. This is a credit risk and customer lifecycle value prediction problem. The data came from Freddie Mac single-family home loan. The ML-based solution is using user behavior patterns, and we are predicting the user risk, which is the loan delinquency risk. So this is an example that is very relevant to cases like student loan delinquencies, which has been announced has gone to 9.1% in some cases. U.S. is facing student loan repayment crisis. It can be repurposed to mortgage loans, student loans, auto loans, credit card loans, personal loans. The partner on this project has been Pluto 7. So there is we basically considered 4 classes of outcomes, and one is safe, where we say that the creditor has been very safe lender, or has been very safe to lend to the person. Second is moderate safe, and the percentages shows that how much of the data was in each of this category. As you can see, very risky, we have very, very little data. So this is a very unbalanced situation where we have large amount of very safe lenders, and a lot of these financial services examples, we have very unbalanced data. That is, one outcome has a very small amount of data. So we took 3 sets of data, and we built multiple models on that. And the results were very good. We used deep learning networks, we used XGBoost, we used random forest, and we used naive Bayes methods. So by using all these different algorithms, we came up with a very good result in which the case 1 is safe and case 2 is moderate safe. The third one is moderate risky, and the fourth one is very risky. Obviously, you want to catch the last 2 very accurately, and we have 99% accuracy on the last 2, the class 2 and 3, which is moderate, risky, and risky. And this was a fantastic result we got. So going to model explanation on this problem, we had, I took the top 6 inputs that were that I'm going to use to explain the models. The first one is recency, which is the number of months ago the customer had a recorded delinquency. I stands for number of months. Frequency, how often did the customer had a recorded loan delinquency value of which category, like 1, 2, 3. Recency I is the category delinquency value with the 0, 1, 2, 3. 0 is most safe and 3 is most risky. Credit score, we all know what that is. Loan to value, which loan to value means what is the value of the asset and what is the amount of loan they took on the asset. Let's say your home is worth 200,000 and you borrowed 100,000, then your loan to value is 50%. So the original unpaid balance of the mortgage and the original interest rate on the mortgage. Again, I can take any one of these 4 values: safe, moderate, risky, and risky. So then going through those 4 examples that I gave, what the regulators look. First one is the feature importance. Second is the positive and negative contributions of inputs. So we found out that recency score of 2 was one of the highest important features, which means that if you were moderately risky before, you have a high propensity of becoming risky. And then recency score of safe means also was a very high predictor of safety, and therefore recency score of 0 and 1 were also very high. Unpaid balance was also one of the high important inputs in predicting the outcome. But that doesn't tell you the whole story. Like I told you that recency of 2 is probably a predictor of risky. Recency of 0 is probably a predictor of safe. So we also want to know which one of these inputs had a positive contribution on the outcome and a negative contribution, which increased the outcome, which decreased the outcome, right? Which predicted risky, which predicted safe. So that's important to know. So we found that signed early increased the risk. So the red line shows that if that particular input increased the risk, and if any other input decreased the risk. So you want to know which inputs had what degree of contribution towards a positive outcome or a negative outcome, and also to what degree. Like signed early had a huge contribution in increasing the risk, and same as the discount, whereas the quantity, how many loans they took, had a very small contribution in decreasing risk. The second thing is to look at the correlations of features. On the left chart, the vertical bars are 15-year mortgage, 20-year, 25, and 30-year. And you can see 15-year loans have higher risks than 30-year loans. Is a deduction you can make out of this original loan term versus the original loan. If you look at the term of the loan and the riskiness, the blue means it lowered the risk, whereas the red means it increased the risk. So 15-year had a high degree of risk lowering and high degree of risk increase. So it had a wide dispersion of wide range of contribution towards risk. On the right side, you can see California loan. I have results on many other cities, so whenever I go make presentation, I can switch to Illinois, to New York, to other places. But here we are talking in California, so you can say California properties have a lower risk, because even though it makes a negative contribution on risk, which means that it increases the risk, but the increase is of a smaller amount. Compared the range of values, the intensity is smaller, whereas any other state, the risk increase of a much higher intensity and the decrease is of a smaller value. So clearly there is a bigger risk, any other state but California. And I don't know if that is true or not, but this data shows that. But so that's a great example. So welcome, Adam. He's going to talk about the second use case, insurance loss prevention. Please. Thank you.
So the use case that I wanted to speak about today to y'all was insurance loss prevention. So here what we had done with a particular property and casualty carrier is they wanted to take a look at the loss likelihood of their particular policies. So there are really three elements that you can consider when you're factoring losses. So that's the frequency that it happens, so whether it will occur or not, the severity of it, so how much will that loss be, and the timing of it. For this particular carrier and line of business in that carrier, the crucial thing for them was whether or not a loss occurred, because the majority of those losses were greater than the premiums, so they didn't necessarily care about the severity. Anytime you had a loss, it would be an issue. To recreate this analysis, so the data would be a little bit different here, I took some open source data that's available through Google Dataset Search, and it was Iowa property and casualty losses dataset. It also contains a little bit information from the surrounding states. So whereas Chanchal chose a active state that we're in, California, I chose one that don't visit too often for conferences in Iowa. But our solution was ML-based, and that's from policy information. And then one component that we added to that was crime score details. So based on the location of a particular policy, the crime score could be different. And what we wanted to do was to be able to predict that policy's likelihood of resulting in a loss. Some examples in terms of why frequency is important, just linked a couple articles in the top right. And then different examples of insurance that are out there where some similar analysis can be done is in property casualty, which we're really focused on here. But also we've seen it in auto, professional lines, and health insurance as well. So first, getting into the data preparation and results. So here we didn't quite have the issues with class imbalance to the same level as Chanchal's use case. But what we saw was that the majority of policies resulted in not having a loss. And then about 40% resulted in having a loss from that data set. Some additions that we made were a loss flag. So in the data set, if you look this up online, it will just contain the value of a particular loss. So we wanted to create a 1-0, since we're really just looking for the likelihood and not the severity. We added some crime score index information, so again, based on the location, which we randomized based on the state that they're in. We just added crime score index data to that. The results that we were able to generate by running just a pretty simple, straightforward random forest here was an AUC of 0.91. And the way that we compared it was with the false positive rate and true positive rate. Basically, at smaller levels of that false positive rate, you want to have a higher true positive rate, meaning those that you forecast or predict as positive are actually going to be positive. Those that we say will lose, that will have a loss, actually do have a loss. So when we look at that at individual threshold levels, if we look at the false positive rate of 1%, we can see that the true positive rate there that we have is 40%. And we expect that to increase over time. So at 10% of the false positives, we'd have 78% of the true positives. So anything really above an equal false positive and true positive rate would indicate a well-performing model. When we go through this process, there are a couple of different ways that we make it interpretable. Some of these we've seen before, so I'll gloss over them at a high level. But the first thing we do, often before we even start modeling, is look at the feature correlations. So understand whether or not there may be a positive or negative effect on the outcome, as well as if any features have correlations with each other as your independent features. So what this will do is shed light on the different relationships that we see. So you can easily see a plot of the data if I go down the diagonal axis from top right to bottom right. Then we can see the scatter plots, which would be between two fields. So if I look at the second row, first column, basically that's showcasing my scatter plot for premiums written versus taxes paid. So we'd expect some alignment or correlation there. And then on the right-hand side of it, so if I look at the first row, second column, I'm seeing the correlation between those two, between premiums written and taxes paid. So this is often how we begin to wrap our minds around the data that we take a look at. The second thing that we do is once we perform the model, and we want to understand a little bit more on that global interpretability front, is we look at the feature importance. So here what we're just looking at is the mean decrease in Gini, and we're able to see that the important features here are crime index, premiums written, and line of insurance. Now, as Chanchal pointed out earlier, a great thing to add to this is going to be your variance, so you can tell sample by sample how this changes. We didn't really have a high variance in this one, so didn't necessarily add them to the visual. But this also needs to be combined with some sort of exploratory analysis to understand the direction. So just because we know a feature is important, so if my crime index is important, to be able to see if I'll have a loss or not. From logic here, I think we can tell which direction it is, but you'd also want some exploratory data analysis to say a higher crime score would indicate a higher likelihood of loss. So this in isolation doesn't do well, but in combination with some exploratory data analysis can act as a way to interpret models. The next one that we wanted to look at was, again, more on that local interpretability front. And the ones that we use most frequently when we're looking at problems that are in tabular structures are going to be LIME and going to be SHAP, as Chanchal already mentioned what those two things are. But here, rather than looking at it at an overall level, one thing that we've found useful in displaying information to customers is looking at it at the observation level. So typically we may see this in customer churn prediction problems where they're trying to identify for a particular customer the specific reasons why that customer might churn. So rather than looking at all data points across all features, we look at one specific observation across the features. So it might be for this individual person that the written premium and crime index are increasing their likelihood of churn. The taxes paid, for whatever reason, might be decreasing their likelihood of churn. Versus their industry that the property and casualty loan was assigned to, increasing it, and the location decreasing it. But understanding that on an individual level, and that it might change from observation to observation when I'm looking at both LIME and SHAP, is extraordinarily helpful. All right, thanks, Chanchal. Now I'll hand it back to you to convert to deep learning.
Thank you, Adam. Such an excellent result. The two use cases. So once again, in each of these use cases, we identified 4 things that are very important to regulators. One is which inputs are important and what is the intensity and the variance of that. Secondly, how do the inputs correlate to the outcomes, contribute to the outcomes in a positive way and a negative way? That is, which one increases the outcome, which decreases the outcome. In Adam's case, it was loss prediction. In the example I took with Pluto 7 was in delinquency, loan delinquency prediction, that's the outcome. So which inputs make it larger, which inputs make it smaller. The third thing, how do different inputs correlate with each other in contributing to the outcome? So for example, you might find that a certain amount of loan may not matter if it is taken from a certain banks. So maybe the large banks control the loan industry. We didn't find that result, but say we could find a result like that. It does not matter what the amount is as long as you take it from these banks, right? Sometimes you see significant results like that, and sometimes you see how relationships between you and the banking makes a difference, and we sometimes find those as important criteria. So the correlation between different inputs, like the person, like the lender, and the person who is lending to, the relationship matters. So those are the correlations demonstrate that. And lastly is how do these different inputs change from sample to sample are very important things. And finally, I'm going to show a very strong and innovative research that came out of Google Research by 2 folks, Nicholas Frost and Jeffrey Hinton. Jeffrey Hinton is obviously very, very, very well known, won the Turing Award just a few days ago. Nicholas is a student, and we thought that this is a very significant result in order to do what is called a deep augmenting of an existing rule by creating a soft decision tree. Let's say you built a complex model. Is my audio still working? Let's say you built a complex model, a deep learning model. But a lot of the time, your regulators will not allow you to use that model. They will say, distill it down to a few rules that you can add to an existing solution that already there, which has passed regulation. We want to add more rules to that. That's what we do. So a typical method to solve this problem would be to take that deep learning network, here's the input, here's the output, and take that same input and output and create a random forest or a decision tree. what happens is that the results drastically drop. And let's say your complex deep learning model did 99%, all of a sudden the decision tree does 80%. So there got to be a solution in between where you take that deep learning model and convert it to rules, but you do not lose the performance to that drastic a degree that you come up with something in between. And this result is that it produces a result somewhere in between. It basically takes the deep learning model and tries to understand what the inner workings of the models are, what the gradients at each layer, so that you can take that and make it into a decision tree. This particular picture on the right is from a game called Connect 4. And so the main idea of the soft decision tree is to augment existing rules, find features that have significant influence on the input, on the outcome, and create a human interpretable rule. So a binary decision tree that has learned filters at each of the nodes, okay, is basically a multinomial distribution function. And then when you do a stochastic gradient on that, which is the backpropagation algorithm by which you learn a deep learning network, then you use a equation like that when you sum a multinomial distribution over all layers of the network, and then you're running a stochastic gradient descent. So what we do is that we took the MNIST data, and then we learned the filters can be understood by a person, and then errors can be easily understood, and then the branch numbers indicate the potential for the classification. This is classification of digits, okay? Then the leaf number indicates the final classification. So what they did in their research, they took this complex decision, the convolution neural network, and they learned layer by layer what the decision was, and they converted that to a decision tree. By that, they got a 96% accuracy in solving it that way. So this chart sort of demonstrates on three examples. One is MNIST, the other is Connect 4, and the letters. So the deep network gave very high accuracy, like 99%. Letters 95, Connect 4 is 87 to 0.7. But when you fit a decision tree, then the performance drops drastically. You can see 87 went to 78%. Yeah, so anywhere from 5 to 20% in some instances, as you can see, 95% dropped to 78. But using this decision tree approach, the soft decision tree approach, we got a result in between. So we created a human readable rule, which you can use to augment your existing rules, satisfy the regulations, but yet you don't have as bad a performance as fitting a simple decision tree. So that's all I have. Thank you very much.